This is the beautiful logo of my university, the University of Salamanca. We have the shaded version and the linear version and these old-fashioned capital letters of the name of the university. This year we have the 800th anniversary, the oldest university in Spain. This is the spring title, a title and a subtitle, Notch-induced anisotropic fracture of cold ground pearlitic steels, and as a consequence of this anisotropy, the associated crack path or fracture path deflection and mixed mode stress state. And the subtitle is a tribute to the Italian painter Masaccio. An introduction, I am going to divide my presentation into 8 parts. Introduction, cold drawing of pearlitic steels, very briefly, because this is continuation of the Urbino presentation. Microstructure evolution during cold drawing, anisotropic fracture behavior in air. I add the anisotropic fracture behavior in hydrogen. Discussion about the relationship between microstructure and fracture behavior, conclusions, and the tribute to Masaccio. Let's go to the introduction, first part. The motivation, as usually, fabrication of high-strength precision steel wire by cold drawing produces progressive orientation of the two basic microstructural levels of pearlitic colonies and lamella, and this creates an influence on the fracture and structural integrity. The same as in Urbino, and this is the aim of the work, a material science approach to the fracture behavior, scientific point of view, and a fracture mechanics approach to the design of pre-stressed concrete structure from the engineering point of view. Very brief description of cold drawing of pearlitic steels. Those attending the Urbino conference know it very well. These are 2 pictures of the cold drawing process in a real manufacturing chain. Progressive cold drawing, I think I don't need this. Passing of the pearlitic steel wires through several dies, an increase of yield strength and UTAs by a strain hardening mechanism. Several dies and produces an increase of yield strength and ultimate tensile stress. This is an schematic of the cold drawing process, 3D picture, and 2-dimensional schematics with 1, 2, 3, 4, 5, 6 reductions. This is typical. Sometimes it's 7, sometimes 8, but this is a typical with 6 drawing steps. What is the consequence with regard to microstructural evolution during cold drawing? This is the consequence. With regard to the first microstructural level, here we have still 0, 3, and 6. 0, 3, and 6 steps of cold drawing. In vertical sides we have the drawing axis, and we evolved from a randomly oriented pearlitic microstructure, a slightly oriented microstructure in steel 3, and in fully drawn steel, heavily cold drawn steel, commercial precision steel, a very oriented and aligned microstructure with regard to the first microstructural level pearlitic colonies. In the matter of the second microstructural level pearlitic lamella, 0, 3, and 6 steps of cold drawing, vertical sides of the micrographs, the drawing direction. Here we have the colonies. A colony is a set with a common orientation of ferrite cementite lamella and different from the neighborhood colonies. Then we have the boundaries of the colonies. They are more or less with elliptical shape and randomly oriented, both the colonies and the lamella. In slightly drawn steel, we have a slight orientation of both colonies and lamella, and in the pre-stressing steel, fully cold drawn material, commercial pre-stressing steel, we have like a micro-composite of lamella, of pearlite and ferrite cementite, fully oriented, fully aligned, almost fully aligned in the cold drawing directions or y-axis. Then a summary of microstructural orientation. We have progressive orientation, alignment, and slenderizing of the pearlitic colonies, this first microstructural level, and in addition we have also alignment or orientation, progressive alignment of the ferrite cementite lamella. This is the second microstructural level, together with decrease of interlamellar spacing, an increase of packing closeness. This is a hierarchically structural material, like music by Johann Sebastian Bach. Structure, you see the Christmas oratorium, you have the main structure in 6 cantata, and any cantata has its own structure of oratorium and so on, choruses and so on. Orientation in the drawing direction and increase of packing closeness. Let's go to the anisotropic fracture behavior in A for notched specimen, then notch-induced anisotropic fracture behavior in A. I introduced the results in Urbino, then very briefly, A, B, C, D. We have very different degrees of constraint or triaxiality. We have axisymmetric notch samples with a circumferentially shaped notch. A, minimum depth, minimum radius. B, maximum depth, minimum radius. This is the highest level of triaxiality or constraint. Stress triaxiality is maximum in B. These A and B are sharply notched specimens. And the bluntly notched specimen C and D, we have C with minimum depth and maximum radius, and D maximum depth and radius. We cover all degrees of triaxiality, stress triaxiality or constraint. This is for the maximum, not maximum, but the second level, very high constraint, notch A. We have an isotropic behavior from specimen 4A, notch A, minimum depth, minimum radius, and 4 steps of cold drawing. We have the microfracture maps, horizontal view, and the vertical profiles, the fracture profiles with clearly anisotropic fracture behavior, fracture path deflection. The crack path is deviated from the original propagation in mode 1. We have this mountain profile resembling, you are going to remember this with the painting Tribute Money by Masaccio, because in the background we have this type of landscape, this type of mountains. Here it resembles a different picture, and 6A, very stepped. Regarding notch B, this is the maximum level of anisotropic behavior. Here we have vertical walls, still 3, 5, 4, 6. 3, 4, 5, 6 level of cold drawing. And we have a profile resembling Monument Valley in the John Ford movies, more than Tribute Money by Masaccio. The highest the level of cold drawing, the highest the degree of anisotropic fracture behavior as a consequence of this microstructural alignment and orientation. We have vertical walls, and sometimes we have two vertical walls with a propagation step and a deflection angle close to 90 degrees. In notch C, we have only an anisotropic behavior for 5 or 6 steps of cold drawing. In this case of 5 steps of cold drawing, this is a slightly anisotropic behavior and heavily anisotropic behavior in 6C. And we don't have anisotropic behavior in notch D. What is the meaning of this? The necessity of both constraint or stress triaxiality and microstructural alignment and orientation to produce fracture path deflection. Only microstructural alignment orientation is not enough. We need constraint and cleavage stress to produce this deflection. Regarding the anisotropic behavior, very briefly, we have cleavage fracture slightly enlarged in 3B, notch B, specimen 3, still 4 steps of cold drawing, and notch B, moderately enlarged cleavage, in still 5 undergone 5 steps of cold drawing, clearly enlarged cleavage, and 6B, markedly enlarged cleavage. And it resembles John Ford Monument Valley, and we could define a Monument Valley profile for the heavily drawn steels. With regard to an isotropic fracture in hydrogen, in notches, we have this behavior. Again, we have an isotropic fracture behavior with fracture path deflection enhanced by hydrogen. And this is the appearance of this fracture path deflection in hydrogen. It's a kind of enlarged or an oriented theory topography surface associated linking with hydrogen embrittlement in pearlitic microstructures. With regard to crack deflection in cracked samples, we have again this hydrogen damage topography, enlarged and oriented TTS, and as a summary of fracture modes in hydrogen, in both notches and cracks, in the presence of notches and cracks, in steel 0 hot roll, 0 degree of cold drawing, we have TTS. In steel 6 heavily drawn steel, HDT, hydrogen damage topography 6, very deformed TTS, theory topography surface. In intermediate states, progressively deformed TTS, And as a summary, we have enlarged and oriented TTS, EOTTS. The apparent deformation that observed in the fractal graph corresponds to a direction close to the axial one, or cold drawing direction. Then let's go to the computer to produce this beautiful fractal graph by enlarging the fractal graph's hydrogen-assisted cracking fractal graph associated with a lower degree of cold drawing, as a kind of virtual cold drawing of the micrographs. This is fractal graph 6, and this is a computer production of fractal graph 6 coming from fractal graph 4, enlarging with virtual cold drawing from 4 to 6. The same happens with any fractal graph, and it resembles Donatello's wooden sculpture texture, this enlarged and oriented TTS. This is Donatello's Penitent Magdalene, and the same happens. This is, of course, you know very well, it is in the Museo della Opera del Duomo in Firenze, one of the master walls, only 2 in wooden, and this is not even better. This is of the same degree of highest quality, San John the Baptist in the Chiesa dei Frati in Venezia. We have to organize a visit then again near Venezia to see again the San John the Baptist, Donatello wooden sculpture textures, enlarged and oriented TTS. Now a discussion regarding fracture in air. We leave the hydrogen-assisted fracture, hydrogen-assisted cracking, and we formulate a basic question for fracture in air. Key question: is there a geometric relationship between the oriented and enlarged cleavage and the conventional cleavage? The idea comes from the hydrogen damage topographies, which are virtually drawn in the computer to obtain the same appearance. The procedure is analyze whether or not the oriented and enlarged cleavage, heavily drawn steels, can be obtained by axial elongation of the fractal graph associated with more slightly drawn steels. The same as we did with hydrogen-assisted damage topography, hydrogen-assisted microdamage. This is a kind of virtual cold drawing, computer-assisted cold drawing, very cold, without condition. Here we have for steel 4, the real fractal graph, enlarged, moderately enlarged cleavage, steel 4 steps of cold drawing, and highest degree of triaxiality, notch B. And this is a 4B star, a virtual 4B obtained by enlarging, by virtual computer-assisted cold drawing of 3B. The same procedure from steel to obtain the virtual fractal graph of steel 5. This is the real, and more or less not very different. You have to be, it's a question, it's a psychological question. For me, they are really similar, but it's not so clear. Virtual fractal graph from 3B to 5B. And the same for steel 6, the real 6B, and virtual fractal graph from 4B to 6B start with virtual cold drawing of the 6B. Then, for hot roll steel, we have a common crystallographic orientation of ferrite in all colonies of the same prior austenite grind. This is well known from the research by Thomson, Bernstein, Hitsaf and Bernstein metal transpapers long time ago. We have the prior austenite grind with different colonies, a common orientation of ferrite cementite in the same colony, and different from the neighboring colonies. We have 1, 2, 3, 4 colonies in one grain in this example. Then the conventional cleavage facet size for hot roll steel, isotropic steel, is related to the prior austenite grain size. What happens after cold drawing? We have a kind of palimpsestus. We have an evolution of the prior austenite grain, but there is no grain. The grain disappeared. Then we have the evidence, the former evidence of grain. What is happening now? We could have the virtual line of this palimpsestus, the former boundaries of the prior grain. It is enlarged and oriented, but we obtain again different crystallographic orientation of ferrite in the colonies of the same prior austenite grain. Then, while in the hot roll steel we have common crystallographic orientation in ferrite in the same grain, now in this palimpsestus, the former grain, we have different orientation in different colonies. Then our proposal is the oriented and enlarged cleavage facet size is related to the slender pearlite colony size instead of the prior austenite grain size. We are finishing with the conclusions before the tribute and an epilogue. And the conclusions are: cold drawing produces orientation of microstructure regarding colonies and lamella in the y-axis direction, vertical side of the micrographs, and producing an anisotropic material. The conventional cleavage facet in isotropic pearlitic steel, hot roll, is related to the prior austenitic grain size. With regard to oriented and enlarged cleavage facet in anisotropic pearlite steel, cold drawn, heavily cold drawn material, we propose the slender pearlite colony sign as the basic microstructural unit governing fracture. This is a new critical fracture unit in heavily cold drawn steels, producing, again, exfoliation fracture, a kind of debonding, typical of anisotropic materials, as Giovanna Gavetta suggested in pipelines. Any anisotropic material could produce this beautiful fracture. Then finally, attribute to Masaccio this beautiful painting in Firenze, Florence in English, the Tribute Mani. This is Masaccio Tribute Mani, MTM, and here in the background it resembles the fracture appearance of the not very cold, heavily cold drawn steel, intermediate degree of cold drawing with notch A especially, because notch B resembles more Monument Valley profile more than the Masaccio's Tribute Mani. And an epilogue, some words in Spanish, a language spoken by hundreds of millions of people. And this is the statue of Fray Luis de Leon in the 800th anniversary of University of Salamanca. He was professor at the University of Salamanca, and he was in jail. This is the beautiful facade, Plateresco facade. This is a kind of Plateresco Gothic, very ornamented, very Baroque Gothic. It's not a contradiction, Baroque and Gothic, different styles. A very ornamented Gothic, beautiful facade at the headquarters of my university, 800 years. And we have the teaching lecture room, the classroom of Fray Luis de Leon. When he returned after being to prison because of yellow people, after several years, he said, as we were saying yesterday, we will say tomorrow, a mixture of tradition and innovation, it should be the University of Salamanca. And finally, the verse in Spanish, qué descansada vida la del que huye el mundanal ruido, what a quiet life for those who escape from the noisy world. That's all. Thank you very much for your kind attention.
Okay, thank you.
Sorry.